Hello, ladies and gentlemen. My name is Aman Khan, and my roll number is E20CSE173. Today, for my theory of computation assignment, we'll be talking about the wonderful topic of minimization of DFA. Today we'll be talking about minimization of a DFA. Some basics first. What is a DFA? Let's see. DFA is basically a deterministic, finite, finite automata. Deterministic finite automata. It is a kind of finite automata. There are many kinds of finite automatas that we know about. Finite automatas broadly can be categorized into two categories: with outputs and without outputs. And in the with outputs category, we have two finite automatas called a mealy machine. How do I scroll down? Wait, let me. Yeah. So it's called this is called a mealy machine, and there's another kind called a More machine. And without output, we have three types: DFA, NFA, and epsilon NFA, which is kind of useless, but still. DFA is a deterministic finite automata. Every DFA is an NFA, but not every NFA is a DFA. So basically, all DFAs are NFAs, but not every NFA is a DFA. That is the case. DFAs generally have more strict set of rules. Every input has to be defined on each of the states. So that is a rule. In NFA, there is no such rule. And basically, DFAs are stricter versions of DFAs, which follow certain rules. Okay, all right. We know what is a DFA. Now we'll talk about minimization of DFA. So for example, I have a DFA. Let's take an example. Let's take a DFA length of string. Length of string is even. Okay, so this is the given question. Length of string is even. All right. Length of string is even. So let's first design the language for it. Epsilon is going to be there, of course. And sigma is given as a comma b. All right. So we have epsilon is going to be there. A is not going to be there. A B, B A, B B. So length 2 strings are going to be there. Length 0 string is there. Length 3 strings are not going to be there. Then length 4 strings are going to be there. So A, B B B B, and so on. All right. Let's design the automata for it. So one possible solution could be something like, since epsilon is there, I can have this, then A comma B, and then I can have another state, and then can have another state, and this could be my final state, and then I could go back. So something like this: Q0, Q1, and Q2. So if I had something like this, this will accept all these strings. Yeah, this will accept all these strings with even length. So epsilon is being accepted because the initial state is the final state as well. Now then, one length strings are not accepted, since a and b is when a and b is given, it is going to q1, which is not a final state. Then as soon as another a and b is given, it goes to a final state where the length is 2. It is going to a final state. Length is 3, comes back, q1 not final. Length 4 goes back to Q2, final state. Again, cycle repeats itself. So we can see this is a possible solution for this given question. Length of string is even. Uh, for a given question, there are infinite DFAs possible. So I can draw this. This has n equals 3. So number of states is 3. I can draw something with four number of states as 4 or 5 or 6 or something like that. I can keep doing it, but there is only one minimal DFA, right? So there's only one solution which has the minimum number of states. So for this question, I can do the same question. I can design the same DFA with not 3 states. I can do it in 2 states easily. So I'll show you the solution to get an idea of what I am saying. So I will design this same thing using 2 states instead of 3. So first state is going to be final as usual, and then this is my q1, and yeah, and a comma b, and coming back a comma b. So this we can see 0 length strings are accepted, 1 length not accepted, 2 accepted, 3 not accepted, 4, and it will keep going. So the same, this is equivalent to this, but I have done this in n equals 2. So I have done it in minimum number of states. So this is the minimal DFA. This is the minimal DFA. Now what we are going to do in this video, we are going to learn an algorithm to convert any given DFA into the minimal DFA. So for most questions, for the for the optimized result, we want the minimal DFA, right? So we will talk about the algorithm which converts every DFA into the minimal DFA. All right, so I'll show you. I'll uh, I'll explain it to you by giving an example. So let's take an example of the same thing, of the same question, which is length of string is even. Okay. So this is the question, and sigma is given as a comma b. This has been given to us. The automata I designed was something like this, going in. This is q0. This is q1. Q2, a comma b, and then coming back to q1. All right, so I have the solution for it. This is an automata with 3 states. So for the first thing we do in this algorithm, we are going to make a transition table. So transition table, all right, a, b, and let's see, we are going to have q1, q0, q1, and q2. So for q0, a, then q1, q0 b, q1, q1 a, q2, q1 b, q2, q2 a, q1, q2 a, q1. So this is the initial state, and this is a final state, and this is a final state as well. So this the first step I did was create a transition table. So I have been given a DFA. Now I made the transition table for it. Now what I'm going to do is I am going to create something called a zero equivalence. What is a zero equivalence, you say? Zero equivalence is basically the final states and the non-final states separated into 2 sets. So I'm going to write them separated. So final state is I have final state as q0 and q2, and q0 and q2 are final states, and q1 is non-final state. So I have written it both of these separately. So zero equivalence done. Now I'm going to do one equivalence. So I will do one equivalence. What is one equivalence? I am going to see if if the states in these sets are equivalent or not, or do I have to separate them? If they are equivalent, they can stay in the same set. If they are not, then they must be separated. So for that, what I'm going to do is I am going to check if, so yeah, so I'm going to check the transition of q naught. I'm going to check q naught, and for I'm going to check for q naught and q2. So q naught on A goes to q1, and q2 on A goes to q1. So both of they go to the same state. Then q naught on B goes to q1, and q naught on sorry, q2 on B goes to q1 as well. So they are going to q1. Okay. So q1 they belong to the same set. Obviously q1 and q1 belong to the same set. So as long as they belong to the same set, we cannot separate them. So q0 comma q2 and q1. So this is going to be my first equivalence as well. Now when the zero equivalence and the one equivalence are same, or in general when the n minus 1 equivalence is equal to the n equivalence, we stop the algorithm. That's the condition for stopping the algorithm. In this case, zero equivalence and one equivalence are same. So I am going to stop my algorithm. Now the sets I got was q0, q2 in one set and q1 in the other set. So what this signifies is that in my minimal DFA, q0 and q2 are going to be one state, and q1 is going to be the other state. So the number of states I'm going to have in my minimal DFA is going to be one and two sets. And how I'm going to draw that? I will go back to my transition table first, and I can see q0 and q2 are one state in my final solution. So what I'm going to do is, wherever I find q0, I'm going to put a q2. Wherever I'm going to find a q2, I'm going to put a q0, q0, and q0. All right. So now this is the transition table for the minimal DFA. This has become now the transition table for my minimal DFA, and according to this table, I am going to draw the minimal DFA over here. So q0, q2, and q1 are going to be my two states. So q0, q1, q0, q1, and q2. So this is my initial state, and on A it goes to q1. Sorry, q0, q2, and q1 over here. So on A it goes to q1. Okay, on giving A goes to q1, giving B as well goes to q1. All right, and then q1 comes to q0, q2, given A and B. So yeah, the same thing that I drew earlier. This is the minimal DFA that we have made. Okay. So this is the algorithm. Now, one quick question, one more example, then I'll leave it to you guys to, do some other examples as well. So let's take something easy. Let's see. Okay, we'll do this question fast. Okay, so we have. Okay, so we'll start with the transition table since we don't have a lot of time. I'm going to draw the transition table AB. I have Q0, I have Q1, I have Q2, I have Q3, and then I have Q4. Okay, so Now Q0, so Q1, uh, Q0 to B goes to Q2, Q1 goes to Q1 and Q3, Q0, Q2 goes to Q1 and goes to Q2 and okay, so Q3 goes to Q1, Q4 goes to Q1 and Q4 on B goes to Q2. So this is my transition table now. So this is homework for you guys. Complete this and we'll talk in the next lecture.